Lecture 13, Seismic Reflection Data. Seismic reflection is similar to echo sounding. If we shout at a rock wall, we get an echo because the densities and sound velocities of air and rock are very different. The sound velocity is proportional to the Young's modulus, E, and inversely proportional to the density, ρ. The acoustic impedance of a material is its density times the velocity of sound in the material, ρ times v. The reflectivity is the ratio of the amplitudes of the reflected and incident waves. It is a function of the acoustic impedances of the two media. In this example, the reflection coefficient is almost 1. In other words, almost all of the sound reflects back to the person, but a very small proportion continues into the rock. What do we actually measure in seismic reflection? We measure the time we made the sound and the time we recorded the echo. The time difference is a function of the velocity of the sound in the media and twice the distance between the source and the receiver. In this example with two layers, there are two reflections. The first one at the time it took the wave to go down to the first layer and return. The second one at the time it took the wave to go down to the second layer and return. Therefore, seismic reflection surveys measure time, not depth. The time recorded is round-trip or two-way time. And to get the depth, we must know the velocity of the rocks. Seismic reflection surveys measure mostly compressional, P waves. P wave velocities in rocks range between 2.5 and 6.8 km per second. Most sedimentary rocks have velocities less than 6 km per second. This figure shows a sedimentary basin with lower P wave velocity, next to basement with higher P wave velocity. Because of laterally varying velocities, the reflector at 6 km depth looks like it has a step on the seismic section, because the waves travel more slowly through the basin than they do through the basement. This is obviously an artifact, and it is called a velocity pull-down. Let's look at this seismic section. The vertical axis is two-way time in milliseconds. The section displays a graben limited by a fault. Here is the fault. To convert this section to depth, we need to know the velocity of the P waves. As a first approximation, let's assume the P wave velocity is 3 km per second. This means that a two-way time of 1 second is 1.5 km. 1 second is about 141 units in the image. 1.5 km in the horizontal is about 48 units in the image. Therefore, the vertical exaggeration of the section is 141 divided by 48, which is about 3. To display the image without exaggeration, we need to shrink the vertical axis to 1/3 of its length. Like this. This is the section without vertical exaggeration. Though we have oversimplified by assuming a constant P wave velocity in the entire section, this example illustrates the importance of vertical exaggeration in seismic sections. A seismic section in time is not a geologic cross-section. The reflectivity at most interfaces in the subsurface is very small. At most interfaces about 99.99% of the energy is transmitted, and 0.01% is reflected. The strategy for dealing with very weak signals is to increase the signal-to-noise ratio by measuring the same point several times. The signal adds up, while the noise is subtracted. The geometry by which this is achieved is shown in this figure. Each panel corresponds to one shot. The black dot, and each point on the reflector with a ray going through it, is a common midpoint or CMP, sometimes referred to as a common depth point or CDP. There are twice as many common midpoints as there are receivers on the ground. As the source advances in the direction of the profile, each midpoint is sampled multiple times. In a complete survey, the number of traces through a midpoint is equal to half the number of receivers. Most seismic surveys use at least 96 receivers. Therefore, the number of traces through any midpoint is 48. Each midpoint is sampled 48 times. The first step to process the data is to collect all traces that go through a common depth point. This is called a CDP gather as shown in the left figure. Notice that although each midpoint has been sampled multiple times, we can't add the traces together because each ray through the midpoint has traveled a different distance and therefore has a different time. Therefore, we need to apply a correction to align the traces, as shown in the figure to the right. This is called a normal move-out correction. The normal move-out velocity is the velocity that lines up all the traces in the CDP gather. After that, we can add the traces to get the signal. This process is repeated for all CDP gathers. The common midpoint processing plots all midpoints as if they were vertically beneath the surface, as shown by the red reflector in the figure. This is fine for horizontal layers, but produces a distortion for dipping layers, because the reflection from a dipping layer is not beneath us, as shown by the pink, true reflector in the figure. The effect of the distortion is that all dipping reflections are displaced down dip and have a smaller dip than the reflector that produced them. The process of migration corrects this artifact. This figure shows a non-migrated and migrated section. The migrated section can be identified because it has broad migration smiles at the bottom and edges. Migration also removes diffractions. The ability of a seismic reflection survey to resolve features in both the horizontal and vertical directions is a function of the wavelength, as illustrated in this figure. The wavelength is equal to velocity divided by frequency. The wavelength increases with depth in the Earth because velocity increases and frequency decreases. Thus, seismic reflection surveys lose resolution with increasing depth. The smallest or thinnest resolvable features in the vertical are about 1/4 the dominant wavelength. This figure shows a limestone wedge within shale. The frequency is 50 Hz, and the velocity is 5 km per second. Therefore, the dominant wavelength is 100 meters. The top and base of the wedge can be resolved until the distance between these reflectors is larger than 1/4 of the wavelength, or 25 meters. At closer distances, the wedge is imaged as a single reflector. This is another example showing a series of faults with increasing amount of vertical displacement, or throw. Notice that the faults with throw less than 1/4 the dominant wavelength are not imaged but appear as a continuous reflector. These faults are sub-seismic. The horizontal resolution of seismic reflection data depends on the Fresnel zone. The minimum resolvable horizontal dimensions are equal to the first Fresnel zone. The figure illustrates the first Fresnel zone for higher and lower frequency. The radius of the Fresnel zone is inversely proportional to frequency. Because frequency decreases with depth, the radius of the Fresnel zone increases with depth, and the horizontal resolution decreases with depth. Consider a discontinuous sandstone body. The segments which are longer than the first Fresnel zone will appear as reflections, whereas those that are shorter will act like point sources and will generate diffractions. This figure shows low and high resolution seismic sections from the Wisting field, southwest Barents Sea. The power spectrum indicates the frequency content of the data. The high-resolution data have much higher frequencies than the low-resolution data, and therefore it images very well thin layers and faults. The last topic I'd like to mention is multiples. When there are very reflective interfaces, such as the water bottom, we can get multiple reflections, or multiples, from these interfaces. The multiple will be displayed at twice the travel time of the primary reflector. Multiples from dipping layers have twice the dip of the primary reflector. We can also have peg-leg multiples that result from the ray path bouncing around between two layers in the subsurface. Can you identify a multiple in this section? It is here. Notice that the multiple dips more than the primary reflector. To learn more about this topic, please read Chapter 11 of Allmendinger's Lab Manual and answer these questions.